Hi, this is Stu Schwartz, MasterMathMentor.com. This is video AB, non-essential 37A. The topic is volume using cylindrical shells, and it covers the AB manual, page 266. We see the graph of y is equal to f of x in the first quadrant. We would like to find the volume when the area in blue enclosed by the graph of y equals f of x and the x and y axis is rotated about the y-axis. We next draw our curve rotated about the y-axis, and the curve will now be symmetric to the y-axis, and now will be defined between negative a and a. It should be clear that when we try to find our volume, this will be a disk situation. Recall that our disk formula is volume is equal to pi integral from x equals a to x is equal to b of r of x squared dx, or v is equal to pi integral from y equals c to y equals d of r of y squared dy. R represents the radius and will either be in terms of x or will be in terms of y. We choose a point on our curve at the end of one of the disks, and we will call the point xy. The decision we have to make is whether this is a dx problem or a dy problem. In this case, it is a dy problem because our disks are stacked vertically. So the radius is x, and we will call that, therefore, some function r of y. Therefore, the volume will be pi, the integral from 0 to b, because that is where our disks will be stacked, of r of y squared dy. Now, sometimes it is easy to solve for x. If our curve were y equals 4 minus x squared, solving for x would be simple. But sometimes it is difficult or even impossible to solve for x. For instance, y equals 4 plus the square root of x minus x. Wouldn't it be nice if we could integrate an expression using our x variable rather than having to solve for x and be in terms of y? Luckily we can, and our method is called the shell method. Another method to determine the volume of a curve rotated about an axis is the method of cylindrical shells. We take a function f of x and rotate it about the y-axis as shown in the figure. But instead of creating a disk, we create a right circular cylinder. This cylinder is very thin. Its sides are like paper. We call this a cylindrical shell. It's like an eggshell. We can draw infinitely many cylindrical shells. Note that they all have different heights and different radii. Calculating volume via the shell method is based upon the idea that we will add up the infinite number of lateral surface area to get the volume of the shape rotated about the y-axis. We draw our graph and also a representative cylinder. We choose a point on the graph xy at the location of the intersection of the cylinder and the curve. Let us call A the lateral surface area of the cylinder. This is the area of the cylinder as we go around it and does not include the top and the bottom. Its formula is A is equal to 2 pi radius times height. So if we take the volume of the cylinder's shell, we now say that that is equal to 2 pi radius height times the change in radius. And the change in radius is simply the thickness of the shell. Therefore, the total volume of the curve rotated about the y-axis is the limit as n approaches infinity of summation I equals 1 to n of 2 pi times the radius I times the height I times the change in radius. We now have our formulas for cylindrical shell volume. V is either equal to 2 pi, the integral from x is equal to a to x is equal to b, of radius times height dx if the region is rotated about the y-axis or a vertical line. Or V is equal to 2 pi, the integral from y equals c to y equals d, of radius height dy if the region is rotated about the x-axis or a horizontal line. These formulas show the advantage of the shell method. Rotating about the y-axis when we use the disk method caused us to have to solve for x, and that was not always easy. But as we see on the picture, we have the point xy on the curve, meaning that the radius is x and the height is y, which is f of x. So we use the top formula, v equals 2 pi integral from x is equal to a to x is equal to b of x f of x dx if the region is rotated about the y-axis or the vertical line. Meaning that if we are rotating about the y-axis, we can keep everything in terms of x. Our first problem is to rotate the region bounded by y equals 9 minus x squared and x is equal to 0 and y is equal to 0 about the y-axis. We will attack this in two different ways. First, our traditional disk washer method, and also then the shell method. We first draw the graph and rotate it about the y-axis and realize that this is a disk problem. We draw a representative disk, and at the circumference of the disk, we chose the point xy. The radius r is equal to x. This is, though, a dy problem because our disks are stacked vertically. So we need to write x in terms of y. This, luckily, is easy. Y equals 9 minus x squared, and x squared is equal to 9 minus y, and therefore x is equal to the square root of 9 minus y. So our volume is pi integral from 0 to 9, because that is where our disks are stacked, of x squared, which is 9 minus y dy. And when we do the math, we end up getting 81 pi over 2. We again draw our graph rotated about the y-axis, but now draw a representative cylindrical shell. Again, we choose a point on the edge of the shell and write it as the point xy. It is best to think of this as a dx problem, as the shell's radius is changing. The radius is x, and the height is a function of x, which is y, which is 9 minus x squared. So everything is now going to be in terms of x. We need to get the limits of integration, so we set 9 minus x squared equal to 0, and that gives us x minus 3 times x plus 3 is equal to 0, and x is equal to plus or minus 3. So our volume can be written via the shell method as 2 pi the integral from 0 to 3 of x 9 minus x squared dx. We use 0 to 3 because that is the smallest radius out to the largest radius, and the radius is the x variable and the height is 9 minus x squared. Doing the integration, we get the same answer, 81 pi over 2. The amount of work is probably slightly easier with the disk method because the integration was slightly easier. However, we will find that with the disk method, it is not always easy to solve for x. And the shell method will many times be easier to use, and sometimes the only way to actually calculate the volume. Problem 2 appears similar. We are asked to rotate the region bounded by y equals 6 minus x squared. X is equal to 0 and y is equal to 0 about the y-axis. This is the first quadrant region of y equals 6 minus x squared. We will first attempt to do this by the shell method because it is far easier than the disk method. We again graph our function y equals 6 minus x squared in the first quadrant and then rotate it about the y-axis. We draw a representative shell and label a point on the circumference of the shell as xy. As shown in the previous problem, this is a dx problem as the radius, which is the x variable, is changing. The height is a function of x, which is 6 minus x squared. We need to find the limits of integration, and we set 6 minus x squared equals 0, getting x minus 2 times x plus 3 equals 0. And since we are only interested in the first quadrant, we set x, get the answer x is equal to 2. Therefore, our volume is 2 pi the integral from 0 to 2 of radius times height, x times the quantity 6 minus x squared dx. We could easily integrate this using the fundamental theorem by multiplying out and integrating each term, and we would get 16/3 multiplied by 2 pi, and our answer is 32 pi over 3. Could this problem be done using the disk method? We start by drawing the curve, and again drawing a representative disk at the point xy. We realize that the radius is x, and since this is a dy problem, we need to write x in terms of y. But that's where the problems are. In the previous problem, it was easy to solve for x. For this problem, it's not so easy. We put all our x's on one side and get x squared plus x is equal to 6 minus y. The technique is to complete the square. We take 1/2 of the x coefficient and square it, which is 1/4. So we add 1/4 to each side of the equation. Getting x squared plus x plus 1/4 equals 6 minus y plus 1/4. We factor the left side and get x plus 1/2 quantity squared is equal to 25/4 minus y. We then take the square root of both sides and get x plus 1/2 is equal to plus or minus the square root of 25/4 minus y. And then solving for x, we get x is equal to -1/2, and we will just use the plus square root of 25/4 minus y because we are interested in the positive value. So therefore, that's our expression for x, and therefore our volume will be pi integral from 0 to 6, because our disks are stacked from y equals 0 to y equals 6, of our radius, which is x, which is -1/2 plus the square root of 25/4 minus y, quantity squared dy. If you choose to do this, you'll probably have to do this on the calculator, and you end up getting the same answer, 32 pi over 3. Here is a good rule of thumb when doing a volume problem. If we are rotating our region about the x-axis or a horizontal line, it is generally best to use the disk washer method because it becomes a dx problem. Capital R and little r and the limits of integration will be in terms of x. If you are rotating your shape about the y-axis or a vertical line, the shell method is generally best. Again, it becomes a dx problem where r and h, and also the limits of integration, are in terms of x. The only downside to the shell method is that when you multiply the radius and height together as your integrand, that expression may not be integratable by the fundamental theorem. However, most likely you will be doing the calculation on the calculator anyhow, so that does not matter. The shell method is not part of the AP exam and is not required. However, it can be used, and it can make certain problems where you have to rotate about vertical lines easier. I strongly recommend to students that they learn it.